Trigonometry, Chapter 4, Graphs of the Circular Function, Section 2, Translations of the Graphs of Sine and Cosine, Video 3, Vertical Translations of Sine and Cosine. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned about combining period changes with horizontal shifts. There were two perspectives, plural. The graph of f of x equals sine of bx minus c has a period of 2 pi over b and a horizontal shift of c over b to the right. Or the graph of f of x equals sine of b times the quantity x minus c has a period of 2 pi over b and a horizontal shift of c to the right. The same applies to cosine, and for plus c, the shift is to the left. The consistent thing was the horizontal shift is represented by the number being subtracted directly from the x, and so if the x has a coefficient, such as in the first perspective, you can factor that coefficient out. In this video, we learn about vertical shifts. For now, we will not adjust amplitude. That will be in the next video. Now, as mentioned previously, to invoke a translation, a shift, we add or subtract a constant to a function. To invoke a horizontal shift, we added or subtracted a number directly to the x. How would we invoke a vertical shift? For example, what can we do to the function f of x equals sine of x to move the graph up 2 units? Well, let's think about it. To move the graph up 2, we would need every point on the graph to have a y-coordinate 2 more than its present value. So whatever the y was, I need it to be 2 more. In general, the output of a function is the y-coordinate of an ordered pair. Thus, to move a graph up 2, we need the function to add 2 as the final operation. With this line of thought, it seems something like g of x equals 2 plus sine of x should move the graph of f of x equals sine of x up by 2 units. Let's investigate via graphs from Desmos. And here they are. The black one is the original, and the second one is with the 2 plus in front. And it does look like the red one is precisely 2 units higher than the corresponding points on the black one. So that's pretty easy. To move down, it would have to be negative. We'll say that in a moment. This supports our conjecture. The graph of g of x equals 2 plus sine of x is the graph of f of x equals sine of x translated up 2 units. The value added outside the function can appear on either side of the function. Also, negative values invoke a translation down instead of up. So for example, g of x equals 2 plus sine of x, up 2 units. But if we switch the order of the subtraction, it's still up 2 units. Notice the plus 2 is not on the x. It's on the outside of the trig function. We could have put parentheses around the x for emphasis there. However, if we have negative 2 plus sine of x, it moves the graph down. And if we have g of x equals sine of x minus 2, it also invokes a translation down. Now, vertical translations can occur at the same time as horizontal translations. For example, consider the function f of x equals 2 plus cosine of x minus pi over 4. This will invoke both the horizontal translation of pi over 4 units to the right, as well as a vertical translation up 2 units. One way to graph this is to focus on the quarter periods of the original function cosine. We can apply both translations to the points on the graph of f of x equals cosine of x to locate the graph of g of x equals 2 plus cosine of x minus pi over 4. So here's the graph of the cosine with its quarter period points labeled. To graph the new function, we translate each of these points up 2 and to the right pi over 4. Up 2 to the right pi over 4. Reconnect, and we have our graph. It's pretty straightforward. Just got to have a good graph to start with and good points to move around. Now, there is another approach to graphing a trig function with multiple translations that doesn't involve a graph until the last step. I'll illustrate it. I'll go ahead and tell you now, not my preference. I'll illustrate it with the function we did before. Here's the other approach. First, you list the quarter period values of the original trig function, in this case cosine, over one cycle from 0 to 2 pi. The original quarter period values of cosine are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Next, you take the argument of the new trig function, which is x minus pi over 4, and put that equal to all of those quarter periods. Then you solve this equation for x. It's actually 5 equations. So we would add pi over 4 to both sides, and hence add pi over 4 to all the numbers in our list to get some new values. These are our new quarter periods for the new function, and we evaluate the function at these values. So all of these go into the function, and without all the song and dance, they come out 3, 2, 1, 2, and 3. You can verify that if you don't believe me. And then you plot these and draw the graph. Now, there's the ordered pairs. You plot them, you draw the graph, you get the same graph as before. Personally, I prefer the first graphing technique. It's visual. It illustrates each translation as it occurs, and you can actually do both translations simultaneously. In other words, back here, I could have moved all these points both up and over simultaneously and gone directly from here to here without having a pause in between. So if you feel like you can go from here to here in one move, then I strongly recommend the graphing approach and not this list the new quarter periods approach. There are some books that really harp on this approach, which is why I included it, not my preference. Now you pause and try the following. Describe the translations of f of x equals -1 plus sine of x plus pi over 2 and sketch one cycle of the graph. Pause the video, give it a try. All right, if you haven't paused the video yet, here's your fair warning. Solutions in 3, 2, and 1. The vertical translation is down 1. The horizontal is to the left 3 pi over 4. And here you see the red graph, which is the black graph, move down 1 and to the left 3 pi over 4.